So, Bismillah, salatu wassalam ala Rasulullah. So we are welcome to the class today, and we, as you can see, we're looking into towards train rule ensemble. So, which is AKA, or also known as stacking. So this is going to be the kind of our focus for the day. It's a kind of a disruptive type of ensemble, because it's totally different from what we'll be talking about. So because here we are not going to be talking about voting, but rather a totally new idea of combining different classifiers. So in order to provide a couple of background for us to be able to understand why and how is it possible to have this kind of a combination system. So we're going to provide a little bit of background. So telling us, I will let us first of all know the different types of the generalized structure of ensemble systems, and how we ended up having something called stacking, which is actually, the name is train rule. It's one of the train rule ensemble techniques. All what I'll be talking about, they are referred to as fixed rule. So all the previous one, they are fixed rule ensemble. Fixed rule in the sense that if you decide to use majority voting, then you have to stick with majority voting for that thing. So if you try to use, okay, I'm going to use the minimum of the probability, or I'm going to use the maximum, or I'm going to use averaging, or I'm going to use weighted voting. So these are called fixed rule. So we have a particular rule that you have to stick to once you build the ensemble. But then stacking is totally different from that idea. Rather than choosing a fixed rule to use, we rather need to train another classifier, which we are going to refer to as the meta classifier as we move on. So as stated, we're going to start with the generalized architecture of ensemble systems, or what some people call multiple classifier combination, so that this will refresh our brain and also make us realize the two types, generalized type we're having. Now, so these are the base learners. We have classifier 1, classifier 2, classifier 3, classifier 4. This is just an example. It can be as many as possible, as you know. So let's say we want to train these 4 classifiers. These are the base classifiers. See, these are the base classifiers, you can see. So, or some people call it also, it could be referred to as weak learners. So, because it is believed that they are weaker than when you combine them together. Now, so to train each of these base classifiers, then you need to either you can use the same feature space, or you can use different feature spaces. That's up to you. We discussed that one before. That we can decide to, okay, we use the feature, if you want to recognize your face, we use feature from the eye, lid, feature from the mouth, feature from the nose. We can decide to combine it. Some features are coming from part of the body, another one is coming from the voice of the person. So for example, if I want to identify people in a better way, rather than relying on the facial expression, okay, I can also use their voice. What if I combine the temperature of their body? So in which I'm using different feature spaces. So you can use the same feature space, and you can use different feature spaces, depending on what is available to you. That is why we say you can use either the same or different feature space. Then in the choice of your classifier, you can use the same or different classifiers, in which is going to lead to what we call the homogeneous and then stroke the heterogeneous ensemble. Now, so also in the choice of partitioning your data, you can also actually use the same or different training sets. We discussed this, in which case we use the same training set to train different classifiers. You should know that. If I'm using the same classifier, then the data set need to be different a little bit. We have to do resampling of the data, so that even though I'm using the same algorithm to train multiple models, but I'm changing the resampling of the data, so that the new training set at every point in time is always generating a new model. But if I want to use fixed number of the same training set, I don't want to do any resampling. I want to use the same fixed training set to train multiple models, then those models need to be different classifiers. So this is what we discussed earlier. So once you train each of these ones, you can see this is in parallel. So we put it here because sometimes you might need to train it in series if you are talking of a boosting system. So in that case, after training this one, we will use these decisions. Our decision will be affected by the outcome of this to develop this, to develop this, to develop this. That's in a kind of a different color. This is only applicable to boosting, the boosting ensemble, whereby we need to know the outcome of one classifier before you move to develop another one. But in the general one, the debugging or stacking is in parallel. So in that case, they can all go in parallel without looking at what you have done to the previous base learner. Now, so what after once you are done with training the base models, now the focus now is this: how do you combine the classifier? Combining classifier. This is where the major issue comes up. You see, so in debugging we use the majority voting. In boosting we use the weighted voting. Now, to combine your classifier, they are generally divided into two types of combination. The first one is known as the fixed rule, which is applicable to bagging and boosting. We've discussed this ensemble, and you can see the video on our platforms. Now, the second type is called the train rule. The train rule. And this is where we have the stacking, which is our concern for now. Stacking is an example of train rule combination of classifiers. So this is a generalized architecture of ensemble system. You can see now that after combining, you can see there's possibility for you to go back to do revision. I can change the classifier, I can add more classifier, I can decide to, so it's like a kind of a tikrar is formed here that is looping, it's generate looping, whereby you keep going around, you can do a lot of modification to your base learner generations and the likes. And sometimes you can make it to become even different level of ensemble, as we mentioned earlier. So know that this is the generalized architecture of multiple classifier combination, which we call ensemble. So the one that is left, we have discussed this fixed rule. The one left now for us to discuss is the train rule. Now, what led to the train rule? Because like I said, train rule totally deviate from what you are used to. Because here there's not going to be anything like voting or whatever. So why do we need to do that? What is the genesis of it? Why do we need to have such a disruptive system? That totally, this is why I used to encourage people that sometimes we might not like a disruptive technology, something that is different from what we are used to. You know, the nature of human being is once we are used to something, we don't want anything totally different from it. But sometimes it's good to try it out because it could be actually what you need to move out of that particular enclaves that you've already captured yourself. So sometimes, and you are going to see as we move on. Now let's look at the fixed root combination. When we're talking of fixed root combination, what comes to mind is the bagging and the boosting. Usually in fixed rule combination, we could have what we call the product or minimum rule. It means we're going to use the minimum output to be selected, or the max or the product of them. We use this if you have independent feature spaces. These are situations whereby this idea can hold independent feature spaces. Different areas of expertise are combined together. Error-free posterior probability estimate. If these conditions are satisfied in the base classifier you have trained, then product or minimum rules might be a good example for you to go for. However, if you want to use the sum, which is the mean, the median, or majority voting, this is what we call majority voting. So in that case, you may need to ensure that equal posterior estimation distribution in the same feature space is ensured. Differently trained classifier, but drawn from the same distribution. You can ensure that the classifier are trained differently. So, however, we still say that this one is bad if some classifier or expert are very good or very bad. Because the idea of this is majority voting. That, okay, we give the same 1-1 vote to everybody, irrespective of your classifier accuracy. It's like treating a full professor of medicine just like somebody who just graduated from medical school. And when you want to take a decision, they have equal rights. This is the problem with this. So if there's a classifier or an expert that is very good, then we are giving it the same vote. And if he is also very bad, we are giving it the same vote, like people who are good. This is the majority voting. They all call them on that fixed combination rule. Then we have the maximum rule. And the maximum rule, this is where we trust the most confident classifier or expert. We trust the most confident classifier or expert. So if our classifier is achieving 99% accuracy, okay, we can give it more vote. A single vote from this classifier is going to be 3, which is the weighted voting we mentioned before. This is called, it comes under the maximum rule. We also say this is bad if some classifier or expert are badly trained. So no matter how excellent a professor of medicine is in deciding the case of medical decision, he could make mistake because it's a human being. Even machine, sometimes trained machine learning algorithm that got 99% accuracy. Let's say I train a model and it got 99% accuracy. The fact remains that it is still making mistake in one. There's 1% mistake coming. So if I say that because you have 99% accuracy, during the voting process, I'm going to give you 3. What if the next prediction happens to be from this error? So we are going to be multiplying the mistake of this classifier by 3. So this is the challenge of this majority maximum rule, in which we give more vote right to people that are experienced. Because the fact remains, even though they are experienced, it doesn't mean they cannot make mistakes. So the maximum rule will be given, will be multiplying their mistake by 3 or whatever factor you have assigned to them. So which means either you go for majority voting or the one that gives weighted voting or averaging, you are still having problems. That is why we lead to a question that we're going to ask, that is it ever optimal? From what we've discussed, is any of them ever optimal? We're going to look at an answer to that. Fixed combination rules are suboptimal. They are suboptimal from a lot of experiments and experiences. Why? We said some of the conditions, you can see that conditions were set before you can use them. There are conditions set out. Some of those conditions are very difficult to ensure when you are training classifier, because sometimes you don't even have control over the classifier. It depends on the nature of the data set. So we say, 1, base classifiers are never really independent. So the product rule is going to fail. You see, you cannot ensure that they are going to be independent. If they can be independent, then that could be good for them, but then you cannot ensure this always. You can't guarantee it. Then also, base classifiers are never really equally imperfectly trained under the sum, median, majority. That is, the idea is that, okay, if you want to use majority vote, we want to assume that, okay, can we assure that every model that is going to participate, they are all good? You see, that's the idea of majority voting. It's assumed that all the participating algorithms, they are going to be okay. They are acceptable accuracy. So we give everybody equal voting rights, 1, 1, 1, 1. But actually, can you ensure that all the trained model will have the same accuracy? It's not possible. Then also, when we go to the product of the weighted voting, where you give more weight, the problem is that it is sensitive to overconfident base classifier. So you put too much confidence in a particular classifier because it achieves 99% accuracy or more. It doesn't mean that classifier cannot make mistake when the test sets are coming in. So which means there's an overconfidence problem, just like we could have overconfidence in a professor that we think I never make mistake, which we all know that is wrong, actually. Anybody can make mistake. So, but the product minimum maximum rule create a situation whereby we will be making mistake of multiplying this mistake of these people in multiple folds. So they come to the conclusion that indeed fixed combining rules are never optimal, that none of the fixed combining rules are optimal. They are at one point or the other subject to one challenge or the other. So this is a kind of a basis that necessitated that, okay, we need to explore something totally different. So we go for bargaining, there's challenge. We go for boasting, there's also challenge. What can we do? Can we ignore this, just voting, whatever we talk about? Now, this is what led us to stacking. And now, this is a pictorial representation to tell us, because why we need to give people the opportunity, we need to give people the opportunity to express their feeling. Not, you don't force them to actually give the final result. Because before you talk of voting, in voting, when you want to vote, these are experts now. These are our classifier 1, classifier 2, classifier 3, classifier 4, classifier 5, 6, 7. They need to decide if it is A or B. So in the voting, we need them to come out and tell us the answer is A. For me, it is A. The second will say, no, it is B. But in reality, there are situations whereby these guys will not be sure what is the actual option they want to choose. For example, this expert is saying it is A. You can apply it to anywhere. In medical, this doctor is saying, okay, there should be surgery for this patient. Second expert is saying, no. Can you say maybe B? It's not sure. You can see it's not categorical like this first expert. This one is saying perhaps A. This one is saying no doubt about B. And this one is totally confused, either A or B. It means it's having a kind of probability of 0.5 for each of them. So it's in this, there's indecision problem for him. This one is saying definitely not A, but he is not saying B. You can see why this one is saying a clear example of A. You know, this is the natural way that human being will treat a system. However, the fixed rule that we have all discussed, they need you in most cases to be very specific and say, okay, look, guy, you need to tell me what is the output of your accuracy of your model. For example, okay, it is 1 or it is yes or no. No, we don't need to force them to do that. If you force them to do that, we are losing some information. So let this man have the right to say, okay, it is 0.5, 0.5. This one is saying definitely not A. It means it cannot say B because it's given like 0.2 to A and 0.8 or whatever value to B. It's not tending towards B totally, but then it's having a higher kind of, it's been optimistic that it might be A, or sorry, that it might be B. So this is a natural thing. So we say, how do we know how sure they are? How do we know their expertise? This is why we say that instead of forcing them to take a definite answer, let us allow them to come up with their own, okay, instead of assign a probability to A or B, just give us the probability for A or B, give us the probability for A or B. Don't tell us whatever you want to choose. Your probability, this one is saying, okay, this is 0.5, 0.5. This one is saying it is A. Maybe the probability of A is 0.9 and that of B is 0.1. Maybe B. Okay, give us your probability. I mean, we are not going to force you to say yes or no. Like we know in some cases, the answer is not just yes or no. Everything cannot be black or white. There's always in between. Now, some of the ensemble method might not give room for this. So we move on to stacking and see how can it assist us to be able to have a kind of decision making close to what we do as human beings. Now, this lets us to clarify this point. Types of information produced by individual or base classifiers. You see, the abstract, there are 3 levels of output that any classifier can generate. The first one is called the abstract level output. Here, a classifier only outputs a unique label for each input pattern. So for every input that you send in, every sample you send in, it's going to give you an abstract level output. Let's say we're dealing with classification now. It's going to tell you, okay, for this one, the output is class A or class B, depending on the answer. How do you arrive at A or B? It doesn't tell us. This is called abstract level output. Then we have the rank level output, where each classifier will output a list of possible classes. This one will say, okay, This is my output. Class A is rank 1. Class B is rank 2. While class C is rank number 3. It will tell you, okay, this is my ranking for these classes you asked me to predict. So it is now left to you to select whichever one you want to use. They give you the ranking of the output in their order of preference. If I'm to select, this will be my choice, followed by this, followed by this. This is called rank level output. And the last but not the least, which is really very useful when we talk of stacking, and this is why I need to clarify this concept before we move to stacking fully, is the measurement level output. The measurement level output. In the measurement level output, each classifier outputs class confidence. See, in the measurement level output, each classifier outputs class confidence level for each input pattern. Okay, like I was saying, sorry. The measurement level output, that is, each classifier outputs class confidence level for each input pattern. So it's going to output the confidence level for each of the outputs. For example, I have, it's equal to say, okay, for class 1, let's have 2 class problem. Class 1, the probability is 0.3. Why this one, the probability is 0.7. This is what it's going to tell us. It's not going to tell us that the answer is class B, but then it will tell us the confidence, the measurement level, that is the confidence that I'm having in them. It could be probability. Every classifier has this value inside them. Because when you train a classifier and you just add the classifier predict something for you, before you make that prediction, there are some things that need to guide it in making the decision. You see, usually there are numbers there that say, okay, for example, you are using k-nearest neighbor. Okay, what is the difference between these? How many of them are closer to it by this? So there are some things that they compare the two, and then they can decide that, okay, I can look at it that this one is having 3, while this one is having 1, so I'm good to go for this. Because this one has the maximum value, I'll choose it, which is class A. This is B. So in the measurement level, we don't want you to just tell us A or B. Tell us what are the values that you have gotten that can indicate that the output should be A or the output should be B. So this is what we call the measurement level outputs. Now, bearing this in mind, in most of the voting ensembles, usually people go for the abstract level because it's just telling us yes or no. So we can easily vote along that particular line. Now, so now having clarified this, now we now move to the train rule combiner, that is stacking proper. So what is it? How does it work? See, the base learner training proceed in similar way like what we have discussed. It could be heterogeneous, it could be homogeneous, it could be combination, it could be, so this is, so you have your training data, of course, with n by n dimension. So we have model 1, model 2, model 3, model 4. It could be as up to model n, up to you, as many as you want. Let's say we have 4 for the meantime. Now, so the idea of stacking is, we've discussed why the fixed rules are not optimal. They are suboptimal because of challenges, either majority voting or weighted voting, whatever we like. But this one is trying to take away the idea of voting. Rather, whatever output this one produces is going to be taken. Your output is taken. So we are going to take this output from the base learners as a new training set for the second level model, which is consisting of the prediction from the first level model. That is, the output of this model, we produce the training data. You know, training data is made up of X and the corresponding Y, which is the target. Now, we use the training data to train each of these, either by the sampling, whatever method you use. Now, the output that this one is generating will become the new training data for another machine learning model now. So now, our X now, we can call it now a special X special now. But the Y will still remain, the target here will still remain, of course, because it's the same sample. So this model have succeeded in transforming our input to predicted value here. So the predicted value will take it as the new input. See, this is the predicted value. It's being taken as new input. for the next level. And I'm going to give an example shortly. So that once we take this now, we have again X, we now call it S special and Y. You know, in training, you always need the input and then the output to be able to check your training if it is fine. So the same thing, we move to the next level. But the only difference now is this training set is now the output of the previous models. So we are not voting. There's nothing like voting here now. That we want to vote that, okay, is it yes or no? How many people say yes? No. We take the output from them and then we use those output as new input. This is new training set. We now send that value to second level modeling. See, second level modeling now. So which we call this is where the idea of the stacking comes in, or the meta model. So let's say here we are using k-nearest neighbor, for example. Here we're using SVM. Here we're using decision tree. Here we're using maybe we're using a logistic regression or whatever method. Now, so you have to select another algorithm now to work on the output from this base classifier and generate the final prediction. So let's say here, because I know SVM, I like to use SVM, I can now use my SVM now. See, I can take in a single SVM now, and now use this new training and training set to train this SVM, and it will give me now the final prediction that I'm having. You can see here now, we eliminated the concept of voting because we cannot rely on voting, either weighted voting or majority vote. So it's saying that take the output from the model and let them be as training for another model. I know question that come to my mind of people, okay, why do I know that SVM will be the best to be chosen? You can do optimization here actually. You see? So you can use SVM, note down the result. You can use another model, KNN, note down the result, and then select the one that gave you the best outcome. Because the aim of stacking is we want to get the maximum accuracy. And that is why in literature, most of the competition they are doing, stacking has been leading. Because it's able to avoid the problem of majority voting and also avoiding the problem of weighted voting. Because those are suboptimal. But it doesn't mean they cannot function. That's situation whereby they also still perform. However, from experience and from literature, stacking has really taken Ensemble to another level. In that it has always been performing better than any of the two because of the challenges that those ones had. Now, let's look at this example to make it a little bit hopefully clearer. This is stacking. Now look at the base learner we already shown. These are the base learners. This is the combining classifier. Now these base learners, the base classifiers, they generate their output. This is the output of this. See, for this one, AJ, we generalize it. So this is the probability of class A given X. This is probability of class B given X. Because to be able to decide, classifier one need to calculate the, let's say I'm using Bayes network. Bayes, yeah. No, Naive Bayes, yeah. Sorry, let me use Naive Bayes. Naive Bayes. Naive Bayes is a classifier that is based on probability. You try to find the probability-based system. So each of these classifiers we have something like, what is your probability of A? What's your probability of B? Which is the output of this probability. That's why we say Y. So now what we do now at the combining stage is we will treat the output from them as new features. This is the idea. The output coming from this classifier are going to be treated as new features for the next classifier that is going to help us in carrying out the final prediction. This is the idea of train combiner. Now, so for this one is YA1. YA1, it is the probability of class A, probability of class A coming from classifier 1. This is probability of class A coming from classifier 2. Probability of class A coming from classifier 3. Probability of class A coming from classifier 4. The same thing happened to class B. This is probability of class B, coming from classifier 1. Probability of class B coming from 2, probability of B coming from 3, up to probability of B coming from 4. You can now see that this output, each of the classifier has produced at least two values. One probability for class A, one probability for class B. So it means for every sample that we are having, we don't care about how many number of trainings, how many feature did we started with here. But here now we're going to have how many feature? This is feature 1, 2, 3, 4, 5, 6, 7, 8. We are now having 8 features. 8 new features now that will be used to train the combining classifier here, which is often called the meta-learner. So that we can have it here. We can then say, okay, my SVM now will be trained using 8 features. What are those features? What is the probability of this one? It will be 0.3, maybe this is 0.2, this is 0.4, this is 0.5, this is 0.7, this is 0.3, 0.4, 0.6. As you know that the probability of A plus probability of B for each classifier must be equal to 1. That is the rule of probability, simple. Now for every sample now, I'm going to have something like this. This is for sample 1. For sample 2, we have another thing. So this output from these base learners are now going to serve as our new features, which if you count them, 1, 2, 3, 4, up to the end is 8. So we now have 8 features. These 8 features now will now be used to train this model that will now generate the final prediction. So the only thing that is constant is the Y. You know, the Y target, that will never change. That is the target that tells us that the original answer to this sample is class A. The original answer to second one is B, up to the end. That one never changes, and that was what I explained earlier. So initially here we have our X, which was sent in with Y, the target for training. But now we're going to have the same thing. Now X special, I call it S special. The same Y is still there, nothing changed in the Y. How is it X special? This X is coming from the output. We now treat the output as features. This is why we got this guy here. That's why I call it X special. So that was why I said it's a kind of a disruptive technique, and it's working really fantastically well. So initially, a lot of kind of people trying to say, oh, how do you do this? Is it going to work? You're using outputs to train another system? Yes, because our target is to take the prediction as close as possible to the final output. And that is what this has succeeded in doing. So in a nutshell, that is what we call stacking. And we have different views of them. We could have stacking. This is stacking. You can see here, you have the training set. We have that training set. You train your model. You have model 1, model 2 up to model M. You have the M prediction. You have prediction from these guys. So now you combine the prediction of this one to train this. We call the meta model. You train this again. See that this use the outputs. Use this output for another training. Use it as training set now. See, something that should come to your mind is mostly this, when you want to use stacking, this predicted output should better to be measurement level. Measurement level. What do you mean by measurement level output? That is, tell us the probability of, you don't just tell us my answer is A or my answer is B. Tell us why you are arriving at that particular A or B. Tell us the probability, which was what we described here as an example. And I hope it is clear. We are following. So another view of this stacking. Another view of the stacking is, okay, you can see, okay, this is the first baseline, the training, you train another one, you train another one. So now this one is contributing its own output, its output, its output, because this second level algorithm. Instead of our usual voting that we used to have, now we don't talk about voting anymore in stacking. Rather, we talk about second level algorithm. So we're going to select one algorithm now. So it can be part of the one we earlier trained. It could be, and it could be totally a new one that has never been part of the training of the base learners. It doesn't matter. However, people might need to optimize. Try to seek for the one that is going to do it better. So use some of the trusted algorithms that are better in this kind of thing, or that are known to have good generalization ability, so that you can select the best. So if I select, I have like this is 3, 1, 2, 3. So why not? Here I can decide to try for SVM, try for KNN, try for as many as 16 or more. Then I can select the one that is able to work for me in this second level algorithm predictive solution. So this is the one that's going to give us the final prediction, the final answer. Unlike in the fixed rule, where we just, once we get the output from these guys, we just do voting and then we get our result. No, there's no voting. Rather, we want to do another training. And that is why what should come to your mind immediately if I say, what is the disadvantage of this kind of modeling? It's going to take a lot of time, for sure, because you are having multiple levels of training and testing of model. So another view of the same concept. So you have the training set, you have the model, you build your model. Of course, the testing set can always check. You have prediction. Then whatever come of the prediction will be used to train another model. This is, you can see now, train another model, and then that model will now generate the final prediction, which is also viewed in this way. You have model 1, the output is serving as new feature for the next second level models. And if you really want to go super level and super disruptive, you can go as far as this. This is a case reference. See it? See, they have been used to win a lot of data science competitions. You can see here, you can see the trained data. These are the feature sets. You can see here they are using feature set. Yeah, for some they are using F1, F2, F3, F4, F5, F6, F7. It could be from different feature space. It could be the same feature space. But what we want to talk about is, look at it here. At the first level, they trained 64 single models. 64 single models. So in the next stage, you can see, you can actually use multiple algorithms again to do stacking. You can train multiple algorithms on the same thing here. And the next stage too, you use another tool to train, train these two using the output from this one again. You keep going to other step 3. It continues until you get a final result. I can make it to be stage 4, stage 5. I keep going until I'm okay with the results, because these things sometimes are done to improve accuracy. This is one of the unique advantage of stacking. It is usually done in order to ensure that the accuracy of the model is at the highest level possible. And that is stacking for us. Now, so we will take questions. So if there are questions, but then maybe let me demonstrate and then we can answer questions. Let us demonstrate how the stacking works from a weaker environment. Let's demonstrate how it works from a weaker environment. So as usual, so open my Explorer. This is so let's open our file. I'm going to open the file, go to local disk, program file, go to my Weka. Okay, open data. Let's use our usual database data. Now, so if you want to use Ensemble in Weka environment, so you go to classifier. So you have loaded your data, you go to classifier. Now go here and go to meta. You see meta. Meta means these are the meta learners. These are ensembles. So you go there in, you look for stacking. You can see stacking here. You see, we've demonstrated voting, we demonstrated bargaining, we demonstrated the other boost or so. So let's select stacking. Now, so once you select stacking, it's ready to go, but now you need to set the parameters. So in the parameter, there are two major, very important things you have to set. You have to set the classifiers. What are the base classifier you want to use? The first, the base classifier you want to use. Then after that, you go to the meta classifier, which is this, the second level, the one that is going to combine the base classifier for you. Now, let's start from this. Let's say here, you choose, you want to use k nearest neighbor, for example. So we can check it, how many k you want to use. You remember 5, make sure you set the optimal parameter, and then you click it, you say add. So you keep adding. Let me add another one. I want to add Bayes net. So I'm adding them. I want to add another one. I want to add maybe, okay, I want to add SVM, SMO, that is a support vector machine. I'm adding it. Okay, I've added 3. Okay, I'm okay with 3. So I've added 3. I don't want these zeros, so I can remove it. You can remove whatever you don't want. Yeah. So now you see it's okay. That's fine. You can see here in the classifier, you can see that it is telling me 3 weaker classifiers already selected. Initially, it was 1, the default one. So you can go in back again. You can add as many as you want. You want to train 64 classifier or 65, whatever the case. Keep adding them one after the other, but don't forget you set the parameter of those classifiers that you are adding to make sure that they are going to perform at their best. This is very, very important. Now, so having done this, the next thing that you need to set is to set the meta classifier. Which one is going to help me do the combination, the train combination? So from my experience, one of the one that can generate more is this. I go to function. I like to use SVM. Let's say I have to use SVM, support vector machine. So then I select it. It can be any model, actually. It can be any model. It doesn't have to be support vector machine or any other model. And I did mention you might actually do a little bit of optimization here by trying to, okay, use support vector machine, use k nearest neighbor, use different algorithm to do the train combiner here. And then compare the result and select the one that is having the best result for you, which is better actually. Excuse me. So when you look, once you select the particular algorithm you want to use for combining, that's the second level now. You set this, you set this, then everything is set. That is fine. So, okay, and then you can click start. So it's going to run those 3 base learners, take the output from those base learners, and use it now to train the next stage learner, which is the one that is going to combine your results. So this is how stacking works and as demonstrated an example in Weka. So if there's any question, then I think we can take question now. So that's what we're going to have about stacking for now. Hopefully next week, inshallah, we're going to talk about some other specificity, what we need to know, something to be careful of when you develop stacking or any other ensemble. And hopefully we'll be rounding up ensemble as a topic by the grace of God by next week. So thank you all for coming, and then wishing you all the best. Thank you.